Welcome back. In this video, we're going to look at examples of using polar coordinates and converting them to rectangular coordinates and vice versa. Let's get to it. All right, so here's our first example. We want to plot the points in polar coordinates. And we have these 6 pairs of polar coordinates that we want to plot in this polar coordinate system. All right, and so let's start with our first point. We have a is equal to 2 comma pi divided by 2. Now remember, for a polar coordinate, the first coordinate is the measurement of the radius r, or the distance from the origin of the coordinate system to that point wherever it is. And then the second value, or the second coordinate, represents the angle theta, which is the angle from the polar axis, which is this horizontal axis. And we always start here on the polar axis and measure our positive angles in the counterclockwise direction. All right, so in this case, our radius, or the distance from the origin, is 2, and our angle is pi divided by 2. And what I always recommend that you do when you plot polar coordinates is to start with the angle and then measure your radius, or the distance from the origin. In this case, our angle is pi divided by 2, and so if we start at the polar axis, we will measure our angle in the counterclockwise direction, or above the axis, because our angle is positive. So pi divided by 2 will take us to this line right here, where theta equals pi divided by 2. That's the same as 90 degrees. So our point is going to be somewhere along this line, and the exact location is going to be determined by the radius, which is 2. And so since that radius is 2, we're going to measure a distance of 2 from the origin. And that distance is represented by these circles. This first circle represents a radius of 1, this second circle represents a radius of 2, and this third circle represents a radius of 3. Now we could extend this system to include larger values of a radius, but in this example we're keeping things simple and only working with 3 circles, or the values for a radius up to 3. But just know that we're not limited to 3. This polar coordinate system could be extended to be a lot bigger. Okay, but since our radius is 2, we know that our point is going to be located along this line at the second circle, where the distance from the origin is 2. We could count 1, 2. And so this right here would be our point A. All right, so that takes care of the first point. Now let's work on our second point, point B. B is equal to 1 comma 4 pi divided by 3. And so let's start with the angle. In this case, we have a positive angle, so we are going to measure that in the counterclockwise direction. 4 pi divided by 3 is an angle bigger than pi, right? 3 pi divided by 3 would be pi. So 4 pi divided by 3 is bigger than pi. And so if we start from our polar axis, we know that we're going to at least make it past pi up until this angle right here, 4 pi divided by 3. All right, so we know that we're going to be along this line, or this angle, but the exact location is going to be dependent on the radius, which is 1, so we know that we are going to be along the first circle, which represents a radius or distance from the origin of 1. So our point B will be this point right here. That's going to be B. We're along the angle of 4 pi divided by 3, and we're at a radius of 1. So that's point B. Now let's work on point C. C is equal to negative 1 comma pi divided by 6. So once again, let's start with the angle. In this case, our angle is positive pi divided by 6, so we're still going to be moving in the counterclockwise direction when we measure that angle. And so if we start at the polar axis, pi divided by 6 is right here, so our point is going to be along this line in some way. However, our radius this time is negative 1, and when your radius is negative, what you do is first find where that point would be if the radius is positive, and then you reflect it to the other side of the coordinate system. So in this case, since we have a radius of negative 1, first let's find where that point would be if it was positive 1, and that would be right here. This would be along the first circle where the radius is 1. So this would be 1 pi divided by 6, but since that radius is negative, we need to reflect that to the other side of the coordinate system, right here. So this point right here, along the radius of 1 and along this angle of 7 pi divided by 6, will be our point C. So that is C. Okay, so just remember, when the radius is negative, you need to reflect your point from where it would have been if that radius was positive. Okay, so that's point C. Now let's look at point D. Point D is equal to 3 comma negative pi divided by 6. All right, now in this case, our angle is negative, so instead of measuring the angle in the counterclockwise direction, we're going to measure it in the clockwise direction. We're going to measure it below the polar axis. So if we have negative pi divided by 6, we are going to measure that angle pi divided by 6 below the polar axis. So that will take us to this angle right here, 11 pi divided by 6. Right, pi divided by 6 in the positive direction would take us to this angle, and so negative pi divided by 6 will take us in the opposite direction to this angle. Okay, so we're going to be along this line in some way, depending on our radius, and our radius in this case is 3, so we're going to be along that outer third circle. So our point D will be right here on this coordinate system. That's going to be D. Okay, so that's point D. Now let's work on point E. Point E is equal to -2 comma negative pi. Now in this case, both the radius and the angle are negative, but our process is still going to remain the same. Start by measuring your angle and then measure your radius. So in this case, the angle is negative pi, so we're going to measure pi in the clockwise direction. Now in this case, that's actually going to be the same no matter which way you measure that. Positive pi and negative pi are going to take you to the same angle because a full circle is 2 pi. So if you go an angle of negative pi, that will take you to pi. And if you have an angle of positive pi, you're also at pi. All right, so we're going to be along this line in some way. However, our radius is -2. So if that were +2, we would be along this second circle. But since the radius is negative, we need to reflect that to the other side of the coordinate system. So this right here, this point, that is going to be point E. That is our point -2, negative pi. All right, that was a little bit of a tricky one. So let me go through that one more time. Negative pi is going to take us to this angle right here at pi, and then our radius is -2. So that would mean if that radius was positive, that our point would be right here along the second circle, but since it's negative, we have to reflect it to the other side. So that is why E is right here. Okay, so that's point E. Now let's look at our last point, which is point F. Point F is equal to -3 comma -3 pi divided by 4. Once again, both the angle and the radius are negative, and so this is going to be a little bit of a tricky point to plot, but it's not going to be too bad. Let's start with the angle. We have -3 pi divided by 4. Since that angle is negative, we are going to be measuring it in the clockwise direction. We're going to start by going below the polar axis, not above. And 3 pi divided by 4 is 3/4 of the way to pi, right? If that was positive, that would take us to this angle right here. So we're going to do the opposite of that measurement by going in the other direction to this angle right here, where we have 5 pi divided by 4. That angle is -3 pi divided by 4. So we're going to be along this line somewhere. It all depends on our radius, which is -3. And so since it's negative, we will have to reflect our point. But first, let's determine where that point would be if that radius was positive. So if we're along this angle and our radius was +3, we would be right here. But since it's -3, we need to reflect that to this point right here. And so this point right here along the angle of pi divided by 4 is our point F. All right, one more time, let's go through that process just to make sure that it makes sense. Our angle is a -3 pi divided by 4. So we start at the polar axis and go below it to an angle of 3 pi divided by 4. Our radius was -3, so we find where it would be if that was positive, which is right here at our third circle from the origin, and then we reflect it because that radius is negative. So that is where point F will be. Okay, so that was point F, which was the last point that we wanted to plot in this polar coordinate system. And so that's it for this example. We have successfully plotted all 6 of these points in polar coordinates. Okay, so here's our next example. This one is slightly different than what we did before. What we want to do is find another pair of polar coordinates that represent the same point. And in this case, we have 3 different points that we want to do this for. And so the purpose of this example is to get you to realize that there are multiple ways to express the same point in a polar coordinate system. This is not like the rectangular coordinate system where there is only one point for every pair of an x-coordinate and a y-coordinate. In this case, there are many different ways to represent a point in the polar coordinate system with different values of r and different values of theta. And so let me show you what I mean with this first pair of polar coordinates. We want to find another pair of polar coordinates that will give us the same point as 1 comma pi. So if we plot that, let's plot this point in this coordinate system. Our angle is pi, so if we start at our polar axis, that will take us to this line right here. That is where the angle is pi, and then our radius is 1, so we're going to be along this first circle. So our point is going to be right here. Okay, so that's the point that we want to represent with another pair of polar coordinates. And the easiest way to find another pair of polar coordinates to represent the same point is to simply just add 2 pi to your angle, right? Because in the polar coordinate system, one full circle is the same as an angle of 2 pi, right? So if we add 2 pi to this angle, our new pair of polar coordinates would be 1, 3 pi. If we were to plot this point, 3 pi is 2 pi plus pi, right? So if we start at our polar axis, 2 pi would make one full circle, and then one more angle of pi would take us to this line right here. And that radius is still 1, so we would be right here at this point. Another way to look at it is if we were to plot this point like we did, we're right here, and we add 2 pi to our angle, that would make us do one full loop, and we're back to this point. So adding 2 pi to your angle is always going to give you another pair of polar coordinates that represents the same point. Okay, so that's one solution that we could find for this first pair of polar coordinates. Again, there are many other different solutions. We could add another 2 pi to this angle and have 5 pi, and that would still be the same point. And then we could add another 2 pi and have 7 pi, and that would still be the same point. And so you kind of get the idea. There are many different ways that you could represent the same point in polar coordinates. All right, now let's look at our second pair of polar coordinates. This time we have 3 comma negative 5 pi divided by 6. And so let's come up with another pair of polar coordinates that represent this same point. But first let's plot this point. Negative 5 pi divided by 6 is our angle. That is a negative angle. So we're going to measure that angle in the clockwise direction. And just as a reference, positive 5 pi divided by 6 would be this angle right here. So we're going to be doing the opposite of that measurement in the other direction. So that will take us to this angle right here of 7 pi divided by 6. And then our radius is 3, so our point will be right here in that system. So I'll plot that point right there. Okay, so that's the point that we're trying to represent with another pair of polar coordinates. In this case, we can do the exact same thing that we did with our previous point. We can just add 2 pi to our angle, and we will represent the exact same point. All right, so if we add 2 pi to negative 5 pi divided by 6, we can represent 2 pi as 12 pi divided by 6, right? 12 divided by 6 is 2, so this would be 2 pi. So if we have negative 5 pi divided by 6 plus 12 pi divided by 6, negative 5 pi and 12 pi will be 7 pi. And of course, we can add those because the denominators are the same. That will give us a point of 3 comma 7 pi divided by 6. Right? And you can see that that's true if you look at this point in this system. If we were to measure this positive angle of 7 pi divided by 6, that would take us from our polar axis to this angle right here, 7 pi divided by 6. And of course, that radius is 3, so we're right here along that third circle. Okay, and so that is another pair of polar coordinates that represents this exact same point. In this case, we also had an added benefit of making that angle positive. Typically, when you represent a point in polar coordinates, you'd like the radius and the angle to both be positive. It makes things a lot easier to work with. And so representing this same point, but with a positive radius and a positive angle, is a pretty nice thing to do. So adding 2 pi to the angle in this case resulted in a nicer point that we could plot. Okay, and now let's look at our last point here. We have negative 2 comma negative pi divided by 3. And so let's start by plotting this point. Both our radius and our angle are negative. Negative pi divided by 3. We will measure pi divided by 3 in the clockwise direction. So we're going to go below the polar axis. And pi divided by 3 in the positive direction would take us to this angle right here. So in the negative direction, that will take us to this angle right here. 5 pi divided by 3. All right, and then our radius is negative 2. So if that was positive, we would be along the second circle right here on this angle. But since it's negative, we need to reflect it to the other side of the system, so our point will be right here. All right, so this point right here is what this pair of polar coordinates represents. Okay, but if we want to find another pair of polar coordinates that represents that same point, we could do a couple of different things here. We, of course, could add 2 pi to our angle, and that would give us the exact same point. But I'm going to show you a different way that we can find another pair of polar coordinates to represent the same point. Another rule that you should be aware of is that you can negate your radius and then add pi to your angle. All right, so in this case, if we negate our radius, we'll have positive 2, and if we add pi to negative pi divided by 3, we'll have positive 2 pi divided by 3, right? Negative pi divided by 3 plus 3 pi divided by 3, that's the same as pi because 3 divided by 3 is 1, so this would be 1 pi. Since they have the same denominator, we would add the numerators, and negative pi plus 3 pi is 2 pi. So a radius of 2 and an angle of 2 pi divided by 3 should represent the same point as this pair of polar coordinates. And so let's test that out. If we have an angle of positive 2 pi divided by 3, we will measure that angle counterclockwise. So that will take us to this angle right here at 2 pi divided by 3. And our radius is 2, so we will be along that second circle right there. We are representing the same point with these polar coordinates as we did with these polar coordinates. So that is one correct answer. That is an example of one pair of polar coordinates that would also represent this point. But of course, there are a multitude of other different answers that would also be correct. There is not one unique solution to any of these problems. Okay, so that's it for this example. Now let's look at some different examples where we actually convert from polar coordinates to rectangular coordinates and vice versa. Okay, so for this example, we want to find the corresponding rectangular coordinates for the given polar coordinates. And here's our polar coordinates. We have 4 comma pi divided by 3. And the first thing that I always recommend that you do when converting from polar coordinates to rectangular or vice versa is to first plot your given coordinates in a coordinate system. That way you have an idea of where that point is, so that when you do get your corresponding coordinates from the other system, in this case rectangular coordinates, you can check to see if your answer makes sense. This is particularly going to be very helpful when converting from rectangular to polar, but it's still going to help us check our work in this case where we're converting from polar to rectangular. All right, and you'll notice that the coordinate system I have here is kind of a combination of the rectangular coordinate system and the polar coordinate system. You'll notice that I have this square grid behind this polar coordinate system, and I also have these axes labeled as the x-axis and the y-axis. But just know that the x-axis would still be the polar axis, and this angle right here would be the angle of 0. Up here would be the angle of pi divided by 2. This angle would be pi, and this angle would be 3 pi divided by 2. All right, I just kind of merged the two coordinate systems together so that we can really see how these coordinates represent the same point. And so let's graph our polar coordinates here. We have 4 comma pi divided by 3, and pi divided by 3 is our angle. So if we start at our polar axis here, since our angle is positive, we're going to measure in the counterclockwise direction. So that will take us to this angle right here, where theta equals pi divided by 3. And then our radius is 4, so we're going to count 4 circles from the origin. So we have 1, 2, 3, 4. That's going to be our radius of 4. So right at this point right here will be our point 4 comma pi divided by 3. All right, so now we know that when we convert these polar coordinates to rectangular coordinates, that the resulting rectangular coordinates should be in this first quadrant of this coordinate system. All right, so let's see if that's true. Let's convert these polar coordinates to rectangular coordinates. And in order to do that, we're going to need to use the following two formulas. We're going to use x equals r times cosine theta and y equals r times sine theta. We can use our values of r and theta from our given polar coordinates to find the corresponding x-coordinate and the corresponding y-coordinate that together will make a pair of rectangular coordinates that correspond to these polar coordinates. And in this case, we know that r is equal to 4 and theta is equal to pi divided by 3. So if we plug these values into these two equations, we can solve for x and y. So what we'll have is that x is equal to 4, right? R is equal to 4 times cosine of our angle theta, which is pi divided by 3. And then we'll have y is equal to 4 times sine of pi divided by 3. All right, now cosine of pi divided by 3, that's equal to 1/2. So x is equal to 4 times 1/2. And 4 times 1/2 is 2, so x will be equal to 2. And then for y, sine of pi divided by 3 is the square root of 3 divided by 2. So y is equal to 4 times the square root of 3 divided by 2. Now 4 divided by 2 is 2, and so y will be equal to 2 times the square root of 3. So I'll write that down. Y is equal to 2 times the square root of 3. All right, and so now we have our x and y coordinates that correspond to these polar coordinates. If we put them together, and I'll do that up here, we will have 2 times the square root of 3, which will be the corresponding rectangular coordinates to these polar coordinates. But just to check, let's make sure that this point will be where this point is in this coordinate system. Remember that this point we found by plotting these polar coordinates. But now let's see if that's the same thing for these rectangular coordinates. So far it looks pretty good because both x and y are positive, which means that we will be in this first quadrant. But let's try plotting the point. Our x value is 2, so we'll be right about here. But then our y coordinate is 2 times the square root of 3, which is approximately 3.46, which I will round up to be about 3.5. So if we go back, our x value is 2, and our y value is 1, 2, 3 and a half. And look at that, we're right at that point that we plotted earlier. So these rectangular coordinates do in fact correspond to these polar coordinates. They both represent the same point, but in different coordinate systems. Let's take a look at another example. All right, next up, once again, we want to find the corresponding rectangular coordinates for the given polar coordinates. And we have -3, pi divided by 2 this time. So our angle is pi divided by 2, and our radius is -3. So if we want to convert this to rectangular coordinates, the first thing that we want to do is graph it in a coordinate system so that we know where it's going to be to check our answer, to make sure that the rectangular coordinates that we find make sense. All right, so if our angle is pi divided by 2 and it's positive, we'll start at our polar axis and measure pi divided by 2 in the counterclockwise direction, right? The angle is positive, so we go above the polar axis to this line right here. Remember that pi divided by 2 is the same as 90 degrees, so that will take us to this angle right here. All right, so this is pi divided by 2, but then our radius is -3, so we're going to treat that as if it was positive and then reflect our point. All right, so let's say that this was +3. Our point would be along the third circle, so we'll go 1, 2, 3. This is where it would be if the radius was +3, but it's -3, so we will reflect it to the other side. So that will be right here. All right, so that's the point that our polar coordinates represent. Now let's convert those polar coordinates to be rectangular coordinates. All right, so we know that r is equal to -3 and theta is equal to pi divided by 2. And we're going to use the two following formulas to convert these polar coordinates. We will use x equals r times cosine theta and y equals r times sine theta. So let's plug in our values of r and theta from our polar coordinates into these equations to solve for x and y. We'll have that x is equal to r, which is -3, times cosine theta, and theta is pi divided by 2. And then we will have y is equal to r, which is -3, times sine theta, which is still pi divided by 2. Okay, now cosine of pi divided by 2, that's equal to 0. So we're going to have -3 times 0, right? X will be equal to -3 times 0, but that's just going to be equal to 0. So in this case, x is equal to 0. Now for y, sine of pi divided by 2 is equal to 1. So y is equal to -3 times 1, which means that y is equal to -3. So our rectangular coordinates are x equals 0 and y equals -3. So if we put them together, we'll have this pair of rectangular coordinates of 0, -3. These are the corresponding rectangular coordinates to these polar coordinates that we were given. But let's make sure that it makes sense. Let's see if we were to plot this point on this graph, that it would be at the same place as the point that we got by plotting these polar coordinates. So in this case, our point is 0, -3. So our x coordinate is 0, so we're going to stay along the value of x equals 0, and then our y value is -3, so we will go 1, 2, 3, and look at that, we're at the same point that we plotted from earlier using our polar coordinates. And so 0, -3 will be the pair of rectangular coordinates that corresponds to these polar coordinates that represent the same point. All right, let's take a look at another example. All right, so here's our next example. This is going to be our last example of converting from polar to rectangular. With the next couple examples, we're going to reverse that process and go from rectangular to polar. But let's go through this process one more time. We want to find the corresponding rectangular coordinates for the given polar coordinates. In this case, our polar coordinates are -2, 9 pi divided by 4. And so let's start by plotting this point in this coordinate system. We want to do that so that we know if our corresponding rectangular coordinates that we find make sense, that they represent the same point as these polar coordinates. So let's plot this point. Our angle is 9 pi divided by 4, and that's bigger than 2 pi, right? 2 pi would be 8 pi divided by 4 in this case, if we're using that denominator of 4. And so 9 pi divided by 4 is greater than that. In fact, 9 pi divided by 4 would be equal to 8 pi divided by 4, which is 2 pi plus pi divided by 4. Since they have a common denominator, pi plus 8 pi would give you 9 pi. All right, so what we can do to measure this angle, since it's positive, is start at the polar axis and measure it in the counterclockwise direction for the angle of 2 pi and then an extra pi divided by 4. Now 2 pi is going to be a full circle, and then this extra pi divided by 4 will take us to this angle right here. All right, so 9 pi divided by 4 is this full angle where we make a whole circle and then an extra pi divided by 4. All right, and then our radius is -2. So we're going to start by measuring +2, and then we will reflect our point to the other side of the coordinate system. So in this case, we know that we're along this angle, and if our radius was +2, we would be along the second circle right here, right? 1, 2. But since that radius is -2, we have to reflect this point to the other side of the system, to this point right here. And so I'll plot that. This is the point that we want to find the corresponding rectangular coordinates for in this problem. All right, so let's work on converting our polar coordinates to rectangular coordinates. In this case, we know that r is equal to -2 and theta is equal to 9 pi divided by 4. All right, but in order to make our calculations easier when we use our equations in this case, instead of using 9 pi divided by 4, we could also just use pi divided by 4, right? Because the polar coordinates of -2 pi divided by 4 would represent the same exact point as these polar coordinates, right? Since 9 pi divided by 4 is a full circle and then an extra pi divided by 4, we could subtract that 2 pi from that angle and be left with pi divided by 4, and this will be the same exact point, right? The angle of pi divided by 4 would take us to this angle right here, but then the radius of -2 will take us from this positive radius of 2 to this negative radius of 2. And so that would be the exact same point. So what I'm going to do is instead of using an angle of 9 pi divided by 4, which is a little complicated when evaluating in cosine and sine, it's not terrible, but it's not as easy as pi divided by 4, I'm just going to replace that with pi divided by 4 because -2 pi divided by 4 would be the same point. It's going to give us the same rectangular coordinates, but the calculation process is going to be simpler. All right, so if we use our equations, we'll have x equals r times cosine theta and y equals r times sine theta. We'll plug in our values of r and theta, and we'll have that x is equal to -2 times cosine of pi divided by 4, and then y is equal to -2 times sine of pi divided by 4. All right, and we know that cosine of pi divided by 4 and sine of pi divided by 4 are both the same value. It will be the square root of 2 divided by 2. So we'll have x is equal to -2 times the square root of 2 divided by 2, and y equals -2 times the square root of 2 divided by 2. All right, now in each case, these 2's are going to cancel out, and so we're just going to be left with x equals the negative square root of 2, and y equals the negative square root of 2. And so together, the x-coordinate and the y-coordinate are going to give us a pair of rectangular coordinates of the negative square root of 2, comma the negative square root of 2, which will correspond to our given polar coordinates. And so let's test that out. If we plot this point, note that the square root of 2 is approximately 1.4, so each of these coordinates would be -1.4. So if we go to our graph here, -1.4 in the x direction would take us to right about here, right? We'd go to -1 and then almost halfway to -2. And then we'd go down -1 in the y direction and then down another -0.4. And that will take us to that same point. right? Negative 1.4, negative 1.4 takes us to that same point that we plotted in polar coordinates. All right, so this pair of rectangular coordinates represents the same point as these polar coordinates, so this is the correct answer to this problem. All right, so this was the last example of finding rectangular coordinates from polar coordinates, but now we're going to reverse this process and convert from rectangular coordinates to polar coordinates. All right, so here's our first example of converting from rectangular to polar. We want to find the corresponding polar coordinates for the given rectangular coordinates, and our rectangular coordinates are 1, the square root of 3. All right, so now just like when we converted from polar to rectangular, the first thing that I recommend that you do here is graph the point that you're given. Make sure you know where it is in the coordinate system so that when you find a pair of polar coordinates, you can check to see that it makes sense and that you have the right answer. And like I said earlier, this is going to be very important when we convert from rectangular coordinates to polar coordinates because there are going to be multiple different ways to express the same point in polar coordinates. There's not just going to be one unique answer. There's going to be a multitude of different answers that you could find. All right, and so let's get started here. Let's plot this point. We have 1, the square root of 3. The square root of 3 is approximately 1.7. So if we go to our graph here, we're going to treat each of these squares as a unit of 1, just like I have in the previous examples. Our x-coordinate is 1, and our y-coordinate is 1.7, so that will take us to about right here. All right, so I'm going to plot that right here. This is the coordinate point that these rectangular coordinates represent that we want to convert to be in polar coordinates. All right, and so now let's work on converting them. First thing you want to do is identify x and y. In this case, we know that x is equal to 1 and y is equal to the square root of 3. And then when you convert from rectangular to polar, we're going to use two different equations. Instead of using x equals r times cosine theta and y equals r times sine theta, we're going to use these two equations. R squared equals x squared plus y squared, and tangent theta is equal to y divided by x. Now the reason we use these two equations instead of the other ones is that each of these only includes one of the coordinates that we need to find for a pair of polar coordinates, right? Only r is in this equation, and only theta is in this equation. We don't have r and theta in the same equation like we did before. And so these two equations are going to make it easier for us to solve for r and solve for theta. And if you're not sure where these equations came from or the previous set of equations that we used, feel free to check out my lesson video where I show where they come from and why they work. All right, but if we use these two equations, let's plug in our values of x and y. We'll have r squared is equal to 1 squared plus the square root of 3 squared. And then we'll have tangent theta is equal to the square root of 3 divided by 1. Now 1 squared is 1, and the square root of 3 squared will be 3. So r squared will be equal to 1 plus 3. And 1 plus 3 is 4. So we'll have r squared is equal to 4. So I'll write that. R squared is equal to 4. And then to solve for r, we can take the square root of both sides and find that r is equal to plus or minus 2. And that plus or minus is going to be important because depending on how you want to set up your polar coordinates, you could have a positive radius or a negative radius. All right, it's all going to depend on our angle. And so let's go back to this equation and solve for theta, our angle. In this case, the square root of 3 divided by 1 is just the square root of 3. So we have tangent theta is equal to the square root of 3. And then to solve for theta, you can go about this two ways. You can either ask yourself what angle is tangent equal to the square root of 3, or you can just use the arctangent function or the inverse tangent function. Because if you take the arctangent of both sides, that will cancel out with this tangent function and give you that theta is equal to arctangent of the square root of 3. And arctangent of the square root of 3 is pi divided by 3. So theta will be equal to pi divided by 3. Okay, so now we've solved for r and solved for theta. Now let's see if we can determine a combination of r and theta that will give us this point right here that corresponds to these rectangular coordinates. And so if we use this angle of theta, pi divided by 3, it's a positive angle, so we will measure it in the counterclockwise direction. Let's start at this polar axis. That will take us to this angle right here. We're already at this angle of pi divided by 3, where it seems to be that this point is located. So let's just use a positive radius That way we don't have to reflect it to the other side, which is not where our point is. All right, so I'm going to choose to use positive 2 and positive pi divided by 3. So let's write those polar coordinates up here. We will have 2 comma pi divided by 3. These polar coordinates are going to represent the same point in this coordinate system that these rectangular coordinates represent, of 1 comma the square root of 3. All right, we have an angle of pi divided by 3, and we have a radius of 2, which would be 2 circles from the origin, which is what we have right here. They both represent that same point. Okay, now this is just one solution to this example. We could find some other pairs of polar coordinates that would also represent this point, right? If we use some of those rules that we looked at earlier, we could add 2 pi to this angle, and these coordinates would still represent that point. We could negate r and then add pi to our angle, and the coordinates would still represent that point. So you could take this a multitude of different ways, but typically it's going to be easiest for you to find a pair of polar coordinates where both the radius and the angle are positive. And so that's generally the direction that I would encourage you to take. See if you can get both of these values to be positive to represent your point in your coordinate system, given a pair of rectangular coordinates. All right, let's take a look at another example. So next up we have this example. Once again, we want to find the corresponding polar coordinates for the given rectangular coordinates. And this time our rectangular coordinates are 0, 3. So this is a pretty easy point to plot. So let's put that on our coordinate system here real quick. X is equal to 0, so we're going to be along the y-axis, and then a y value of 3 takes us to 1, 2, 3 right here. So those rectangular coordinates represent this point right here. Okay, so now that we plotted our point, let's work on converting these coordinates to be polar coordinates. In this case, x is equal to 0 and y is equal to 3. And so we're going to use those values in those two equations that we can use to convert from rectangular to polar. And those equations look like this. R squared is equal to x squared plus y squared, and tangent theta is equal to y divided by x. All right, so let's plug in our values of x and y into these equations to solve for r and theta. So we'll have r squared is equal to 0 squared plus 3 squared, and tangent theta is equal to 3 divided by 0. Now 0 squared is 0, plus 3 squared will be 9, because 3 squared is 9. So we have r squared is equal to 9. And then if we take the square root of both sides, we'll find that r is equal to plus or minus 3. 3 and negative 3 are both the square root of 9. All right, so that's r. Now let's work on theta. We have tangent theta is equal to 3 divided by 0. But we can't divide by 0, so how can we solve for theta in this equation? Right? 3 divided by 0 will be an undefined value. Well, if we think about this logically, if tangent theta is going to be equal to 3 divided by 0, which is undefined, we just have to ask ourselves, where is tangent undefined? And if you're familiar with the tangent function, you know that tangent is undefined at pi divided by 2. The graph of tangent theta, if this right here is pi divided by 2, will look something like this. It's not a perfect drawing, but there's going to be an asymptote here at x equals pi divided by 2. Or in this case, theta equals pi divided by 2. And so because there's an asymptote at that value of x, that is where this function, the tangent function, is undefined. And so, in this case, we will say that theta will be equal to pi divided by 2. That is the angle that results in tangent being undefined. All right, so we have r equals plus or minus 3, and theta equals pi divided by 2. And so let's see which one of these values of our radius makes sense given this angle. If we were to plot a pair of polar coordinates that have an angle of pi divided by 2, which is a positive angle, we would start at this polar axis and measure that angle in the counterclockwise direction to this angle right here at pi divided by 2. And notice that we are in the correct angle where our point is when we plotted our rectangular coordinates, and so we don't want to reflect to the other side, so we're not going to use a negative value of r, we're going to use a positive value of r. R equals positive 3. So our polar coordinates will be 3, pi divided by 2, and those coordinates are going to represent the same point that our rectangular coordinates represent, right? We have pi divided by 2, and then a radius of 3, so let's count our circles, 1, 2, 3. We are at that same point. And so these polar coordinates correspond to these rectangular coordinates. And once again, this is not a unique solution. There are plenty of other pairs of polar coordinates that would also represent that same point. Like I explained in the previous example, you could add 2 pi to this angle and your coordinates would represent the same point, or you can negate the radius and then add pi to your angle and your coordinates would represent the same point. But once again, it's easier just to give polar coordinates where both the radius and the angle are positive and your angle is as small as possible, meaning that it's not bigger than 2 pi. So this is the most common answer that you will see for a problem like this, but just know that it's not the only possible answer. Okay, and so that is it for this example. And so let's look at one more example for this video where we convert from rectangular coordinates to polar coordinates. All right, so here's our last example. We once again want to find the corresponding polar coordinates for the given rectangular coordinates. In this case, our rectangular coordinates are -2 times the square root of 3, comma -2. And so let's start off by plotting the point that these rectangular coordinates represent. In this case, x is equal to -2 times the square root of 3, and y equals -2. And 2 times the square root of 3 is approximately 3.46 or 3.5. And so if we have -2 times the square root of 3, think of that as -3.5. All right, so if our x value is -3.5, we'll go 1, 2, 3, and a half. And then a y value of -2 takes us 1, 2 here. All right, so this point right here is the point that is represented by those rectangular coordinates. All right, and so now let's use our x value and our y value to convert these rectangular coordinates to polar coordinates. And so let's use those two equations. We have r squared is equal to x squared plus y squared, and tangent theta is equal to y divided by x. And so if we plug in our values, we'll have r squared is equal to -2 times the square root of 3 squared plus -2 squared, and then we'll have tangent theta is equal to -2 divided by -2 times the square root of 3. All right, now if we work on this equation first, let's square each of these values. If we square -2 times the square root of 3, we'll be squaring -2 and we'll be squaring the square root of 3. -2 squared is +4, and the square root of 3 squared is 3. So r squared is equal to 4 times 3 plus -2 squared, and -2 squared is 4, so we'll add 4. And 4 times 3 is 12, so we have 12 plus 4, which is 16. So r squared is equal to 16, and then if we take the square root of both sides, we'll have that r is equal to plus or minus 4. The square root of 16 is plus or minus 4. All right, so that's r, our radius. Now let's work on theta, the angle. Notice that we have -2 divided by -2 times the square root of 3. Those -2's will cancel out, and so we'll have tangent theta is equal to 1 divided by the square root of 3. And now if we take the arctangent of both sides of the equation, that will cancel out with tangent on this side of the equation. So we'll have theta is equal to arctangent of 1 divided by the square root of 3. And arctangent of 1 divided by the square root of 3 is pi divided by 6. So theta is equal to pi divided by 6. Okay, and so now we have r and theta. Now we just have to decide whether it makes sense to use +4 or -4 given this angle. All right, so if our angle is pi divided by 6, let's go to our polar axis. Pi divided by 6 is positive, so we're going to be measuring in the counterclockwise direction. So that will take us to this angle right here, pi divided by 6. And if our radius is positive, we'll go to the fourth circle. So we'll go 1, 2, 3, 4. But that's not where our point is, right? Our point is on the other side of that angle. So we want to use -4 as our radius instead. All right, so if we have these polar coordinates of -4 comma pi divided by 6, that's going to represent this point. We go to pi divided by 6, that's our angle, and then we count to +4 and then reflect the point. So we're along this angle, and then 1, 2, 3, 4 circles, and then we reflect to the other side, and now we're at the same point that we plotted from these rectangular coordinates. And so these polar coordinates of -4 comma pi divided by 6 correspond to these rectangular coordinates. And this is just one possible solution. All right, and if you remember, I did say earlier that it's preferable to get a positive radius and a positive angle. In this case, we don't have that, which is okay. This still represents this point. But if you did want to have both a positive radius and a positive angle, what you can do is use one of those rules from earlier in this video where you can find equivalent points in polar coordinates. What you can do in this case is negate this radius and then add pi to your angle. So if we do that, we would have positive 4 and then 7 pi divided by 6 as the angle, right? If we add pi to pi divided by 6, that would be the same as adding 6 pi divided by 6, and 6 pi plus pi is 7 pi. All right, and so if we were to plot this point, our angle is 7 pi divided by 6, and it's positive. So if we start at the polar axis, we'll measure this way until we get to 7 pi divided by 6, this angle, and then we have a positive radius, so we will count 1, 2, 3, 4 circles. All right, so either of these pairs of polar coordinates would be a correct answer to this problem. And of course, there are other answers as well that would also be correct. These are just the two that I decided to show in this video. Okay, so both of these polar coordinates correspond to these rectangular coordinates. They all represent the same point in a coordinate system. Okay, and so with that, this was the last example for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.